by the river water. A little bit of let's say redundancy is by connecting these three plants with the pipe system. And on the lower left, you can see that we are building up another system until 27 with more cooling abilities at the cogeneration plant, where we already make district heating and the energy. From our last plant, here's a picture where we made some installation to expand the district cooling system in the city center, and the plant on the lower left side will have around 36 megawatt cooling ability. As I said before, we have around 100 customers with 87 megawatt and around 25 kilometers of network in the streets. As I said before, we are using the streams in Munich. Mainly it's from the Isar, and there are remaining underground streams with the water from the Isar, and we use it to recool, which is mainly for the efficiency. So we take out the water and transport it to the plants where there's a chiller, refrigerant machine that is doing the recooling, or in the winter time we use heat exchanger to make direct cooling, which is very efficient. As you can see, the whole system is very efficient. So we have a primary factor of around 0.3, which is very good, and the customers accept that and use it for their buildings. Yes, a technically generated cold, and in the winter time, direct cooling. As I said, there are many advantages, and one main advantage is the ecological one over the running water, direct cooling, and so on. We made an evaluation of our first plant, and we made the situation like this. We have 50 megawatt district cooling, and on the opposite side, it would be the self-supply. So we looked and compared these two technical systems, which one is efficient and how much. And as you can see, the megawatt hours year on the left side, and the energy need for supplying that cooling demand over district cooling is the light blue. And in comparison to that, the red and yellow ones are the self-supply with old and new machines. As you can see, we have energy savings with the district cooling from around 50 to 70% compared to self-supply. That has included all components like the pumps and so on. The second system is the groundwater use. Here in Munich, there's a lot of geothermal potential because the groundwater is running from the Alps northways underneath Munich and several streams. It's around 10 meters beneath the surface. and we try to use it in many places as possible in Munich. That's why we made some evaluations with a technical university in Munich and with this city and so on, to have as many data as possible. Here you can see it. Underneath the surface, around 10 meters, there's the groundwater. It has around 11 to 13 degrees. And we try to use it. In one way, it's we extract the groundwater with a culvert or well and transport it in pipes to the buildings where we use a heat exchanger for direct cooling, or if necessary, we use chillers for example, if the customer needs 6 degrees. A well is known, but a culvert, I will show you later what that exactly is, but it has something to do with the subway here in Munich. We have underground lines on the subway in Munich, and it's mostly on the same level as the groundwater. So there's a system that's called a culvert. It collects and transports the streaming groundwater underneath the tunnel and injects it on the other side, so that no groundwater is flowing into the tunnels. And we use that system by extracting the groundwater, transport it to the buildings where we make the cooling, and re-inject it, heat it up, or if we use heat pumps, we lower the temperatures and we inject it into the stream again. Of course, not in every place there's a underground line, so we use wells as well on public places. As you can see here, one of our system, that was the first system we installed in 2004. That's BMW, where they have high cooling demand around 5 megawatts for their data centers. That's around 250 liters a second. And we extract the groundwater by culverts and wells, and have a pipe system around 5 kilometers to the data center. And it runs around 20 years with no problems. Very good system. As you can see on the lower left, it has a very high energy efficiency ratio, around 24. That's why, because we don't need chillers, we just supply the BMW data center with groundwater, and there's only energy needed for the pump and nothing else. On the lower right side, you can see the culvert. There's the water, the collected water that goes underneath the subway. And here we place our pump in it and connect it to the pipes, as you can see on the upper right. For groundwater, we use plastic pipes. Unisolated, because the groundwater has the same temperature as the soil around, so we don't need to isolate the pipes. As I said, we not only use the system for cooling, but also for heating. So mainly we install the system for cooling. And in addition to that, we install heat pumps at the customer's building. So we can use the system in 2 ways. And also there's a need to equal, let's say, the temperature in the ground, because if we are allowed to use the groundwater, it says not only for cooling, but for heating. So the groundwater will have around the same temperature as we took it out before. I have here another example from a customer. The customer said, we are going to build 2 buildings and I need cold and heat in around those temperatures. And as you can see here, the megawatt he needs for his buildings. And so we looked around, how can we do that? Yeah, we have a little bit of groundwater that we could use. So we made hydrogeological investigations and planned and constructed horizontal and vertical filter wells in public places and the network. In addition to transport the groundwater to the buildings, we installed chillers and heat pumps for the cooling and heating demands. And in addition to that, district heating, because he needed around 0.7 megawatt of 70 degrees, which is better with district heating. And since we installed that system, we are doing the operation of the network and the systems. As you can see here, the right side, it's a technical center with the heat exchangers, the heat pumps, the chillers, and so on. And in the middle, you can see that we're not only delivering the groundwater and the temperature with chillers and heat pumps, but we also use some heat and cool shifting inside the system. It says when you have, for example, data center in the building, which also every time produces heat, also during winter time, we move that heat to the other side where it's needed, for example, for heating the building in the winter time. And also we do the same thing to the other side and during summer when cooling is needed. So it's a very interesting combined system. And yeah, it's running since several years and we have very good data from it. Another system is in the north of Munich. Here we have installed wells at it's a Dantebad, that's a public outdoor pool. And we take out 120 liters a second and transport it via pipes to computing and service center, as you can see on the upper right. And not only are we doing cooling here, but we also use the waste heat on several occasions, like example on the upper left side here, we have a bus depot and the surface on the outside, there's no need to clean it during winter time from snow and ice, because we use the waste heat from the data center to, let's say, heat up the outside floor. And so there's no need to clean it, and we can use it in an efficient way to make it ice and snow free during winter time. Also, we use the waste heat for the staff apartments in the kindergarten, because there the waste heat is used for heat pumps we installed. The last thing is the waste heat is also used at the public outdoor pool to preheat the water in the pool. So it's a very combined system and very interesting. These are only 3 from our 8 groundwater systems. As I come to the conclusion, here in Munich, we have installed a lot of district cooling systems, and we expand all the time and have many more interested people who like to connect their buildings to our systems. So it's very interesting technique and very efficient. So yeah, it's quite interesting. So that's the end of the presentation. Thank you for your attention. And if you have any questions later on, I'll be pleased to answer it. Thank you.
Thank you very much, Patrick. That was very cool. And it's always very cool to see such diverse applications and in particular synergies with other types of buildings and leisure activities even. I wanted to just quickly open the floor if anybody has a clarification question, because there was quite a bit of technical detail, I guess, on the slides. So if anybody is more and technically minded. We do have one question in the chat that I think maybe we should take. How does taking water from the river affect the river? And do you return the water later in the process, or is it a closed cycle? Thanks, Meglena, for the question.
Thank you for the question. I think it's connected to that. I will see if I have better. Yeah, here. When we take out the water from the river, we have strict restrictions from the city that says, no overheating and so on. That's why we installed recoilers in addition to that. And when we reinject or reintroduce the heated water into the river, it has quite no effect, because it's just a small, let's say, piece of water which we heat up, and when we re-inject it and mix it with the whole river, there's an upheating, let's say 0.3 degree in whole. So it's not very much. And in addition to that, we have restrictions from the city that says not too much heating, let's say.
Yes, indeed. Always good. Thank you very much indeed. I think we can now move on to maybe Julia's presentation if she's ready.
I am. Thank you so much. I actually had a couple of questions for Patrick myself, because it was such an interesting presentation. But I don't know if it's the right time, or I should leave them for later on.
If you can stay to the end portion of the Q&A, I think maybe
Sure.
it's better to have a discussion then, and you can absolutely abuse your privilege as a speaker there and take.
Yeah, I took advantage of that. Okay, so then I'll move on. Thank you so much for having me this afternoon. I'll share my screen in a moment. Here we are. Sure, I know it takes a moment. So my name is Giulia Conforto. I'm a senior researcher at eThink Energy Research, which is a non-profit research center based in Vienna that was originated a few years ago as a spin-off of the Technical University. We focus mainly on the decarbonization of the built environment, upgrade and transition of heating and cooling systems, pre-feasibility studies of district heating and cooling, modeling of heat demand at the local, regional, national level, and also at the European level. What I will show you today is a series of tools that have been developed in the framework of the Cool Life project. Now, cooling is not even the elephant in the room. Cooling is usually the small sister that is not even regarded as a need or as an issue. If you look at the European policy, you have quite some consistency in the streamlining of heating and cooling being mentioned together in the last few years, but that's a recent development. And then if you move to the national level or the local policies, heating is the big need. Heating is the sector that is the largest consuming and emitting sector in Europe, but cooling is disregarded, which is tricky because with growing temperatures, we know that cooling needs are growing, as Patrick was showing a moment ago. Now, when we talk about summer indoor comfort and cooling of lived inhabited spaces, we mostly think about air conditioning. Lately, we started thinking about heat pumps, but there are so many other solutions that are commonly not even considered. if not disregarded or just not known. Passive cooling, free cooling, nature-based solution, building insulation. There are a lot of possibilities. There are lifestyle and behavioral changes that can reduce the cooling demand. Just to give you a minor example, you keeping the shading on your windows during the day and opening the windows as soon as after the sunset, when the air freshens up, is a kind of lifestyle behavior that costs so little, makes so much sense, and does reduce significantly the cooling demand. The fact is that so far we were used to do it when we were taught that, but we never really thought about collecting all these changes that all together can help addressing the growing need for space cooling. So this is where the project Cool Life comes in. Let me see if okay, perfect. So the project Cool Life is a life project that is about to end towards the end of the year in October, and has developed two main outcomes. A tool, a GIS-based open access analysis tool that provides a number of U27 datasets that are open access. So that's quite interesting as a basis for analysis, and for including space cooling into local heat planning and local energy planning, because this is also one of the things that we have seen in many years of supporting municipalities in the development of their energy strategies, is that heating is tackled in the local energy transition strategies, but cooling, sometimes it's mentioned, most of the time it's not even mentioned, definitely it's not tackled as an issue as important as heating. And the other outcome of the project is the Cool Life Knowledge Hub. This is a repository of quality controlled data and publications relevant for space cooling. Now, this is a quick overview of the consortium, so you have an idea of the partners, which are highlighted in green, and the case studies and social innovators that are highlighted in blue. We are 8 partners throughout Europe. And this is an overview of the issues and barriers that we have identified and how the project has addressed them. So for the lack of space cooling visualization analysis tools, there's the Cool Life tool that we have developed. For the lack of data and information, or the UI, the data set that we have made available, not only as a data set downloadable from an online repository, but also visualized through the Cool Life tool. For the lack of knowledge on comfort, lifestyle, and user behavior, impact on space cooling needs, as well as legislation and regulation, technologies and measures, available financing instruments. For all of these aspects, we have developed a number of reports that are available on the Knowledge Hub. I'll show you in a moment. And then for the lack of knowledge about the current barriers and the drivers for innovative space cooling, based on all these reports, we have developed a series of recommendations for policymakers and regulatory bodies. Now, what is interesting about the Cool Life tool that I'll show you in a moment is that the Cool Life tool offers a number of calculation modules that can be used individually, but can also be used in a tool chain to develop a scenario analysis. Now, I'll move to let me see if I can stop sharing this slide and then share the other screen. So I'll move to the Knowledge Hub directly. Okay, share. And Anna, I don't know if you received my slides with the addresses. Otherwise, I can put the address of the Knowledge Hub directly in the chat, as you prefer.
No worries. I can copy paste that in the chat, and we'll also send them afterwards as well.
Perfect.
Don't worry about
Perfect. Let's zoom a bit out so you can see better. Are you seeing my website or not yet? Or are you still seeing the slides? It's on the wrong screen.
No, it's the
sorry.
website. It was the website. I was all good.
Ah, was it? Okay, sorry. Apologies. I'll do it again. Because the control was still on the other screen. So this is the Cool Life website. On the first page, you find an overview of what the project does and the tool and the Knowledge Hub, how they can help various stakeholder groups and the upcoming events. Going back up, In resources, here you can find all the publications that we have developed during the project. So the knowledge base for occupant-centric space cooling is a database compiling insights on behavior, preferences, and interaction with cooling system to enhance energy efficiency and comfort-driven solution. Then we have the analysis of behavioral interventions, which is a review, of course, of behavioral-based strategies that are implemented across Europe to promote sustainable cooling. The taxonomy of space cooling is a structured classification of space cooling technologies and measures, assessing their characteristics, their readiness level, and their potential for sustainable implementation. The energy demand assessment is an evaluation of the energy demand for space cooling across different climates and building times, considering trends and influencing factors and efficiency improvements. The impact assessment is explanatory, is a study of the environmental, economic, and social impacts of various space cooling solutions to support decision making. Then we have a review of financing schemes, which is a comprehensive analysis of all the European and national regulation financing instruments from the public side, but also private financing products that were offered when we ran the assessment last year throughout the EU27 for sustainable cooling. And it goes hand in hand with this data set, which is basically a collection of about 600 instruments. Then we have this multiple socioeconomic impact of sustainable space cooling, which is an assessment of how sustainable cooling solutions can affect different socioeconomic groups, addressing their affordability, health, and equity considerations. And last but not least is the review and mapping of regulations on sustainable space cooling, which is a comprehensive analysis of the policies and regulations at the European level and at the national level, run over 10 member states. So that's the difference with the financing one, which is on the EU27. Next, well, good practices. It's a series of good practices distinguishing between what can an individual do as a consumer or as a public authority, and specifying the difference between active systems, passive systems, and lifestyle comfort and behavioral changes. And then what's on you find the upcoming trainings. The Knowledge Hub is this curated library of 50 resources. I can open one of them. You can search them through the search bar or open them one by one. They're listed on the page, and for each one there is a collection of metadata. So what kind of publication that is, the authors, and where we retrieved it from. And then we go to the tool. Now, I don't know if you are familiar with Hot Maps. That is a GIS-based tool that was developed with the Horizon 2020 project, and that has been used consistently for the development of the comprehensive assessment in a series of countries, which recently has been updated by another project, which is CityVats. Now, the Cool Life tool uses the same framework for the same tool framework. So the map looks the same, and the selection tools are the same, but what changes there is the selection of layers and calculation modules. So it works like this. We can choose anything. Let's go to Munich, since we just saw it. Munich. You can search it through the search bar or zoom in to the location. If it goes, found it, perfect. You can choose the statistical level at which you want to run your analysis. Let's say we want to do it at LAU2, so at the municipality level. As you select the box, you see you can select the statistical box, or you can draft a square, a circle, a polygon, which are useful for smaller areas to identify a smaller area and do a very precise analysis. Then you can load all these default data sets, which are listed in layers. So you have the cool density total, and then you have a 2020 baseline, a 2030, 2040 and 2050 scenario with 3 variations: baseline, moderate efficiency, and high efficiency, which are useful for the scenario analysis. Then you have the heat density total, the gross floor area. Those are distinguished between residential buildings and non-residential buildings. And then you have the share of gross floor area by construction period. And then you have a series of climate indicators like the cooling degree days and heating degree days. Let's, for instance, if I go to the cooling density total, this is gonna open up. And as you can see, there is a color coding in the legend here. If you go on I information, there is a link to the repository where you can go and find a description of the data set, and you can download the data set. Going back, you can also download the default dataset from here or download the your layer selection. Now, if I go to the calculation modules, we have 5 calculation modules for the individual cooling supply, 1 for district cooling, and then the policy and financing mapping. Now, the first one, I'll go quickly through them because I don't want to take too much time. The first one is a calculation module that basically extracts the current cooling needs and cooling density. And what it is useful for is that it can scale up or down the current cooling needs. And you can download a raster file with the scaled result, which you can use for your future scenario assessments. As you can see, the results are loaded here in the right side of the screen. Then the technologies measures is a calculation module that allows to estimate what would be the effect of a certain rate of uptake of active cooling solutions, be it air conditioning or heat pumps or else, with a specific seasonal energy efficiency rate, and where you can choose between 3 options of the 3 scenarios: the no measure, low adoption, and high adoption. And for each one of these calculation modules, if you have generated previous raster files, or if you have your own raster file, you can upload it. Up here, you can import some inputs, or down here, if you have saved them by generating them with other calculation modules, you would find them here available. So, for instance, with the default values, we have set an uptake of 7.5% of the residential gross floor area and of 23.5% of the non-residential one, with 2 quite similar seasonal energy efficiency rate, and you find the results to the right. I'll move on with the next one. The comfort, lifestyle, and user behavior calculation module allows you to choose among 3 types of measures: traditional lifestyles, country-specific summer thermal comfort requirements, and interventions that have proven as best practice to reduce space cooling demand. So if you go opening the basic inputs, you can choose to display all measures or be country-specific only. And for the type of behavior, you can see the effect of various behaviors that have been assessed in the report that I mentioned earlier. And then again, you can choose what kind of buildings you want to focus your analysis on, and what kind of behavioral intervention you expect to support, to introduce. So feedback and information, nudging, monitoring incentives, or policy. Let's say I run the calculation module, and you have the results to the right. So for instance, among the traditional practices, you see that window shading, blinds, curtains, or shutters are used in the country, and the use of natural ventilation, and that the recommended summer indoor comfort temperature is between 25 and 27, which helps you develop scenarios for your cooling demand. And also you do have a section with the charts where these results are also indicated in a graphic manner and can also be downloaded. Moving on, we have the economic feasibility, which compares the economic assessment of individual decentralized cooling systems compared to centralized district cooling. Again, you have a number of inputs that you can tweak if you have, if you know what they would be in the specific area of your assessment. And if I go back to the indicators, one moment that it's loading, I hope. Yes, here we are. So, of course, the indicators that you select in the calculation module generate a certain scenario. So as you tweak them, that affects the results. And you have results concerning the useful energy demand for the baseline scenario and for any other scenario you have selected. And then the effect on the final energy demand and on the useful energy demand, and an estimation of the levelized cost of energy from passive measures and for the scenario measure. Next, we would have the demand side management is a module that works on the net zero level. So for a moment, I will select the whole Germany. This is a module that allows to estimate what would be the effect of supplying the electricity needed for the active space cooling technologies directly with the integration of photovoltaic panels on the rooftop of the buildings that consume that electricity. So how to remove that pressure from the power network that supplies the whole city. And here you have the non-PV cooling demand in the business as usual scenario, and then the one non-optimized and optimized. Now, if you want to know what are the assumptions behind all these scenarios, there is a link here to the top right to the wiki. And if you go to the wiki, of course, you have a description of all the functionalities of the tool. And if you open the calculation module section, demand side management, here there is a page that links you to an online tutorial. We have a series of tutorials on YouTube. So if that's easier for you to access this information, and then a description of the methodology and the publications that describe the complete scenarios, what kind of input and output you can expect from that calculation module, and how to run a sample run. So what do you provide as input and what do you obtain running the module? Moving on to the last CM. Just a second. Close here. Go back to Law 2, reselect Munich, the district cooling one. Now, this is a calculation module that assesses the economic feasibility of some district cooling networks in a selected area, considering a given electricity price, number of cooling days during the year, the COP of the district cooling supply and the individual cooling supply, and discount rate and lifetime of both systems. You also have a section of advanced level input where you can provide more specific information if you have that for your region. And concerning the cooling density map that you use to run this calculation module, you have the default dataset, or you can use our estimation of the cooling needs by 2030, 2040, or 2050, given the baseline or moderate or high efficiency of individual cooling systems. Of course, what happens is that the higher the electricity price, the less convenient will be individual cooling supply, and the more convenient will be a centralized cooling network. The higher the number of cooling days, or the higher or lower the COP of those two of the two systems, it will change significantly which areas are considered feasible for a district cooling. Let's have a look. I choose the cooling density total by default. Let's see what comes out of this calculation module, because I haven't run it recently, so I don't remember it. Sometimes it happens that in the present time with the given default data, you don't find any boxes that are actually considered interesting or feasible for a district cooling network. But if you do the same estimate for 2030 or 2040, you do start finding areas, because of course the cooling demand is projected to grow. Now, what you see here in the map are those boxes that are highlighted in orange. That means that in those areas, the calculation module has found an anchor. Usually that is a healthcare facility, like a hospital. So a structure that has a consistent cooling demand 24/7. And around that, the calculation module identifies other building blocks, which are considered as visualized as boxes of a hectare per hectare. And they are then considered in the assessment of the total theoretical cooling demand and the estimated actual cooling demand and the potential for district heating and the peak of the area, and then an estimation of the costs and the average levelized cost of supplying the district cooling and of the individual supply. This brings us towards the end, the last two calculation modules. I don't know how I'm doing with time, Anna. Am I running late?
Yeah,
Do I still have a couple of minutes?
if you're if you're close to wrapping up, then take the time. All good.
Good. Then we also have charts in this calculation module of the district cooling showing the potential of the theoretical cooling demand, the actual cooling demand, and district cooling coverage potential compared to the overall cooling demand in the area. I would be curious to ask Patrick if the boxes that the calculation module has found are actually in areas that they have considered in their actual network. But then again, we probably have used different number of cooling days and electricity prices and so on. Maybe I can finish showing the last two calculation modules and then we come back to this. The policy one is not really a calculation module, it's more an interactive layer. So it works on any level between the NUTS 1 and LAU 2, but the data is provided at a national level. You have an overview of the national background and strategy, and you can export the file. So if I go to exporting the file, let me open it. Question is, I don't know which screen it will open now. Of course, not in the one that is shared. Just a second. Okay. Fine. What? I'll have to download it again because for some reason it opens the financing mapping. Have I opened the legal and regulatory information? Okay. Sorry, I'll run it again. I might have confused the export extra files. I might have confused the download. 3. Okay. Okay, now I understand. Sorry. The file was right. I just opened it on the wrong tab. That's why. Okay, so this is what you obtain from the mapping of a policy and regulatory frameworks. You have a summary of the country policy landscape. Then you have a focus on the draft NECP update, on the comprehensive assessment of 2020, on the building regulation, and then you have an extract of the public financing schemes and the private financing schemes for that country. Then you have also one tab on the National Energy Strategy and Policy for Adaptation. And here you have just the list to understand how we categorize that. And that is, this kind of export is available for 10 countries in Europe. While if you go back to the last calculation module, which is the one of financing, here you can filter it for including or not European schemes. And if you want to see only the public or the private schemes, let's say we want all schemes for Germany, I run the calculation module, it's going to give me, that's very good, an error. Nice. Try again. Something went wrong. Okay, we'll try again in a moment. Sometimes maybe a lot of other users are using the tool in the same time, and sometimes the queries go wrong. Basically, what you obtain is an overview of the private and public financing schemes that are available in that country. In the result box to the right, do it again. And no, I don't. Okay, I'll show you from the I'll show you from the resources. Let's do it this way. And that is a filtered export of this overall mapping, which is an Excel file. Okay. These days my laptop is a little bit overwhelmed. Okay, it's opening just a moment. Basically, okay, here we go. Let's go on public schemes. This is a collection of all the public and private financing schemes that we could find relevant for space cooling. You have an overview in the cover of what you will find inside. Now, for the schemes that we found, Germany is one of the most prolific countries in Europe, by the way, in terms of number of schemes. For each scheme, you have the indication of the level, if it's European, national, regional, or local. And for the regional and local, you also have the indication of the region or city. You have the scheme in English and in national language, the sectors for which that is relevant. If yes, if they cover that sector, yes, in brackets, if they are not meant to cover that sector, but in some cases you could still use it. So just don't exclude it, have a look at it. Then the type of in building, residential, non-residential, the type of a scheme, if it's a loan, a grant, some technical assistance, a guarantee, an equity investment, or an energy efficiency obligation. In that case, it's not relevant for consumers, but it's relevant for energy companies. Then you have a main link and any other relevant link to read the full documentation about the scheme, when it started, and a short description of what is financed through that scheme. And for the private schemes, we couldn't find when they were started because it's simply not an indication you find in the bank's website, but there is the list, there is the name of the bank providing the scheme, which is interesting because if you know that one of these financial institutions in your country issue a product that is relevant for the decarbonization of buildings, they most probably have an office dealing with green finance. So especially if you're a project developer, you know that they will have someone to talk to for finding a customized solution. So still gives you an indication. And since this mapping suffers from a very fast obsolescence, there is a tab of mapping sources. So each source that was used to put together this mapping is listed country by country with the keywords that we used. So in this case, for Germany, you see down here we have the NECP, the Recovery and Resilience Plan. Then we have the Comprehensive Assessment and the Long-Term Renovation Strategy, the National Energy Efficiency Action Plan, and the Building Renovation National Contact when available, and then a series of national entities. For Germany is Klima- und Transformationsfonds. Then we have the ministries that are relevant for issuing financing for the decarbonization of buildings and heating and cooling, and the investment, development financing agency, and other websites where you can find most of the schemes. The point is, if some of the schemes you find in the mapping have been discontinued and you want to know what has been introduced to substitute them, these are the links where you are most probably going to find information about it. So this brings me back to sharing my last slide, which would be asking for your feedback. Okay, here, and I'll share. In the set of slides that I've shared, there is actually more than what I've showed you today, because there are also the use cases and how each one of them is structured, but there was no point in showing them all to you today. So let's go to the very last slide. Opala. Here we are. If you might take 1 minute and provide us some feedback about what you think about the training, what you think about the tool, if you think it's going to be useful, if you see yourself using it in your future work, that will be greatly appreciated, because as a European project, it's important for us to know that we meet stakeholders' needs. And that would be all from my side. Thank you for your attention.
Great, thank you. Anna, I don't know if you'll take, or I should pick it up.
I'm here. I disappeared for a second because, of course, technical problems would always get in the way. But thank you so much for that very detailed presentation. Just in the interest of time, I'm going to say maybe everyone can put questions in the chat if they have any for Julia, but we can move on to Neil's presentation.
Yeah, absolutely. Sorry, Niels, for taking longer.
No, that's all right. That was very interesting. And I'm sure everyone's going to have a play around with the tool, which is much, much easier always to, get the presentation and then start playing around with the tool. Thank you, Neil, for starting to share. Yes, we will send presentation slides after the event. Absolutely.
Okay, right. Thank you for the opportunity to talk today, and thank you to everybody for joining this presentation. I hope it's of interest. I've got going to try and cover quite a lot of things today, so I may go a little bit quickly, but please, any questions, as already mentioned by Anna, put them in the chat, and I'm happy to pick them up a little bit later. So let's get on to it. Who are Alfa Laval? Well, we're quite a large international company. We have sales companies in 55 different countries, and we have a number of different production units, 37 in total globally, and 100 service centers and over 21,000 employees. So our products are mainly in thermal transfer and hydraulic separation, so various types of plate heat exchangers. Again, you can see an array of different products there, and this really means that we can select the right product for the job rather than actually trying to sort of bend the project to fit the actual product itself. So we have such a variety. So where do we fit in a district cooling project? Well, what you can see here is a very stylized graphic of a district cooling system, and you can see that our products are normally installed anywhere around the sources of cooling, whether that is aquifers, whether it's lakes, rivers, etc. Some hydraulic separation required. Also in plant rooms, in chillers, and so on and so forth. Very often also installed as pressure brakes in different places, and then normally in substations at the individual building level. So right across the whole chain from source to use. District cooling, it's got many benefits that I'm going to cover. It allows you a much more varied energy source, and that's one of the key aspects we see with all types of district systems, that you may be very limited when you look at the individual building approach, but actually when you look at that on a network, then just the sheer geographical location of all the pipework and geographical things that may be around, like lakes and rivers, gives you much more diversity to use different sources. And we can see here, this would be a typical substation application in the base of the building. And as we move through the different options, this is one which I'm going to show a little case study at the end, but this is free cooling. You have some plate heat exchangers here to the district cooling plant and then distributed out. That's exactly what's been done in Toronto from Lake Ontario, which we'll look at a little bit later. And that gives you major benefits in terms of the COP of the overall system itself. And then we have other applications where we're using absorption chillers and maybe absorption heat pumps to do various different things. And this is an area that I'm going to focus on a little bit more as we move forward, because what I want to try and do is demonstrate that energy is energy, and we restrict ourselves if we start to think about only heating or only cooling, and even only electricity. Energy is energy, and we can create any from any of those energy sources. And that's going to become really important when we look at the sustainable city. So cooling is no longer a nice to have. Somebody mentioned earlier on about the increase in cooling demand. It's growing almost 3 times the rate of district heating. And the drivers for that are obviously climate change. And we can see here that everything, pretty much every reasonable KPI measure is showing an increase. So the frequency of heat waves is increasing. So that's the number of heat waves per year. They're increasing. The average length of the heat waves, again, are increasing. And the average length of the individual heat waves in days is also increasing. And one fact I was told by a climate scientist not so long ago, being in the UK, that it is expected that the climate in London will be the same as Madrid is today by 2050. That's the size and scale of the change that is coming, that we need to plan for now, so that we can address it. And obviously, I'm not going to read through those bullet points, but the result of this increase in heat is there for everybody to see, and it's we need to address it ASAP. So, if we look.
I think we may have lost Neil there. For a second, I thought it was just my internet.
No, yes, it was only
I see
mine.
some confused faces, indeed.
Ah, damn.
Just as he was giving us some great context to the issue of cooling. Well, until we get Neil back, perhaps it's worth, Julia, if you had those questions for Patrick.
For Patrick, yes.
Just until I managed to touch base with Neil, I'm going to try and see where he is.
It looks like he reconnected. No, Patrick, the 2 questions were this. You were showing us how you take advantage of the ground source water around your metro tunnels.
Mhm.
And there was a section seen from above where you basically go down with a number of horizontal drilling. And I was wondering, so you already get to the level of the tunnel, but Neil is back. Sorry, Neil, we were filling the gap when you reconnected. You're
Exactly.
muted.
Indeed.
You're muted, Neil. Wait, Neil, you're still muted. Patrick, I'll write my questions in the chat, and then we take them later.
Mhm.
That's
Let's do
a good
this.
idea. They might also be questions other people have, so it'll be good to collect them.
Yes, now we can hear you, Neil.
That's good. We'll get there in the end. And is my screen sharing okay?
Yes, it is. All good.
Let's go again. Right. So when we look at the individual approach, we can see here some of the aesthetic issues that we'll come across, as particularly if you look at individual apartment buildings, you see this kind of thing. But there are many other negatives to this approach to cooling. You lose your diversity that comes with the district approach. So you have to be able to supply instant electricity as those peaks change, and you get a very spiky demand profile as people switch these units on. So you have a reduced or zero diversity compared to the district approach. It's very slow to roll out. It's often not feasible in certain buildings, and it needs a significant increase in electrical infrastructure. And while there is an infrastructure increase, of course, for district cooling, many studies have shown that the cost is actually less than the infrastructure upgrade required for the electrical grid if we look at the individual approach. So it actually is cheaper and it's faster to get us to net zero to use the district approach. And there's an increase in something called the heat island effect, and that is shown here. This is a rather unusual graph showing Paris and the surrounding area. What we can see from the black line is the ambient temperature at night here. And you can see it increases around Paris compared to the suburbs. And that's just because the buildings themselves store the thermal energy from the sun during the day and it's released in the evening. So you get that anyway. But if we add into that individual air conditioning units, and we have the different options shown here, we can see they have an effect on the ambient temperature. They increase it. That's the heat island effect. And the problem with that, of course, is you're now getting almost into a self-feeding negative spiral where adding individual air conditioning units raises the ambient temperature. So you need more cooling units, which raises the ambient temperature even more, and so on and so forth. So how do we address it? Now, these two graphs are actually looking at district heating in Sweden, but the same rules apply because of that ability that district energy has of utilizing multiple energy sources, low carbon sources. And we can see here on the graph on the left-hand side, the amount of energy supplied into buildings via Sweden's district energy systems, and they've increased dramatically from 1970 up to 2022. But if you compare that to the graph on the right-hand side that shows the corresponding carbon emissions for that increase in energy, you can see it's dropped massively down to a very, very low carbon level that it currently is now. So my argument is that the only proven method of large scale or wholesale reduction in carbon is actually from a district approach to energy. So many benefits to district cooling. It is the facilitator that allows for or increases the options for sustainability, and it is agnostic of the energy source. It optimizes energy use while eliminating the need for individual chillers, reduces greenhouse gas emissions, etc., and allows for free cooling from lakes or rivers. And most studies tend to show that the district systems are 30 to 50% more efficient than the individual approach. So you may have noticed I mentioned district energy a lot rather than district heating or cooling. And that's because we need to think, as I mentioned earlier, of energy in a much more wider way. And what we should see are two energy grids in terms of district grids, district heating and district cooling, feeding into the city. You then have a variety of sources that are utilized because the district system is completely agnostic of the energy sources. And then you're providing via substations in the buildings the heating or cooling into those buildings. There are certain technologies like the data center that sits across both grids, taking cooling from the district cooling system and then putting its return temperature, its warmer thermal energy into the heating system. So energy is starting to be shared across those two grids. The district systems can also be thought of as thermal storage. The pipes in the ground are thermal stores, and that allows you to take from that thermal store when there is either no renewables or when there's some lower carbon sources that can be utilized. And the effect of that thermal store, you can charge it at times when you have the energy, and when the energy is non-existent or less than required, you can then take from the thermal store. So those pipes in the ground allow you to peak shave the peaks of demand. And the more you smooth the demand profile, the more renewable energy you can integrate into that. Because as a generality, renewable energy sources normally struggle to modulate based on demand at any kind of speed. They're like constant demand that they can churn away for long periods of time. And the thermal storage aspect allows you to do that. Because of the diversity that's applied in the sizing for both heating and cooling, that also allows you to have less as a total demand, because the building simply won't require all cooling at the same time or all heating at the same time. So there's diversity applied to that. And of course, a really important point is that the waste heat can also be utilized via ORC plants to give you electricity. And as I say, the pipework becomes that thermal battery. And there are many studies that show by far and away the cheapest form of energy storage is thermal storage. So some more implications to this. I'm using the Heat Roadmap Europe here, and I've focused around Spain, not for any particular reason. I just got some data on that we'll look at in a minute. So this is showing you where the excess heat is across most European countries. And we can see the vast majority of countries have an amount of excess heat. That's available energy that we can use. And we can, if we have a thermal delta, whether it's positive or negative compared to ambient, we can provide heating or cooling. And that's a really important aspect when we start to look at waste heat. And if we do that, and this is a prediction by the University of Aalborg on the amount of available waste heat we'll have by 2050. We already have today 2/3 of the energy we require to heat and cool all buildings we waste already. That is expected to grow to about 4/5 by 2050. So this is our required demand based on current insulation levels, current airtight levels, tightness levels in buildings and so on. If we optimize our buildings, we can reduce our demand here. And this is the total amount of expected available waste heat that it will be available in 2050. And you can see we're very close to achieving a parity where we'll have as much waste heat as we actually need to heat all buildings. I won't go in on this presentation into where that heat is, but it's important to note that this was available waste heat. And the definition of that was waste heat that is easy to capture. So I've hinted at why that's important, because once you have waste heat, you can use absorption heat pumps, absorption chillers to produce cooling. Now, this is a map of Madrid, so I'm sticking with the Spain theme. This is PETA 5.2, and you can see this shows the cooling demands basically in and around Madrid, and the colors represent the amount of cooling required. If we overlay over that available waste heat, we can see we end up with lots and lots of arrows all pointing in various places. We can see there is iron and steel production down here. We have paper and printing in 2 different places, a lot of waste heat from that. We have power plants with excessive heat in different places. And then we look on the sewage or the wastewater side, we can see there are significant wastewater options as well, where there's waste heat. And again, to repeat, that wasted heat can be turned into cooling. That's the important aspect, really. And when we overlay that graphic with the available renewable energy and waste energy, we see that we can actually cover the vast majority of Madrid's requirements just from the waste energy that we currently are wasting. And that is not a 2050 slide. That is as of 2022. So significant opportunities there to provide cooling from the waste heat that we already have. So I mentioned earlier that district cooling networks are increasing. They're increasing significantly, much higher than the rate of district heating for those reasons we talked about, and a few other things here about the understanding of the impact that heat has on the human body. And of course, the challenges are financing, construction costs, all the usual things. The market today is about 31 billion US dollars, and the largest market in Asia Pacific, which has a annual growth rate of 9.7%. The fastest growing market is actually the Middle East and Africa at 13.2%. And there was a recent study in India that came to two conclusions. And one of those conclusions was that cooling in India is going to become a human right that everybody will need to have access to. And currently in India, only 5% of the population have access to cooling. So there's a massive increase required there. The second conclusion from that report was that the only feasible methodology to give that, or to increase the amount of cooling to such an extent, was the wide-scale uptake of district cooling, because of limitations in the electrical grid from supplying the individual approach, but even from the point of view of getting enough individual air conditioning units to be able to actually install the amount that they wanted. And of course, the free cooling options that district cooling allows to take away effectively from the demand on the electrical grid. So I mentioned I'd talk a little bit about efficiency. There is only one rule of thumb that we look at, whether it's heating or cooling, and that is the maximization of the delta T. That's the difference between the flow temperature out and the return temperature coming back. The greater that difference, the greater the efficiency of the network. This little equation here, very basic, says that the power you need, the flow rate you need is based on the power required divided by your thermal transfer coefficient times delta T. So the bigger the delta T is here, the smaller the flow rate is that's required to provide that amount of energy. And the reason that is incredibly important, and more important than most people realize, because it allows you to reduce diameters of pipe, valve diameters, fittings diameters. So you're reducing capex on the system. It can reduce the size of your thermal stores. It certainly reduces the size of your pump, and that has an impact on pump energy use. And because pumps operate on the laws of affinity, for every 50% drop in flow rate, your electrical demand drops from 100% to just 12%. So massive pump saving from reducing that flow rate. So there's many capex and opex benefits in reducing increasing the delta T. And that has an impact on system inertia, response times, and all these things. So they all add together and they all compound each other. And by far and away, when I discuss this with engineers all over the world, the problem is low delta T syndrome in buildings, whether it's cooling or heating, it doesn't matter. And the very first question is always, how do I find out where the problem is? How do I find out why I've got low delta T syndrome, and how do I fix it? So I've tried to address the most common aspects on the next slide here. It's about maximizing that delta T. So we need to think about bypasses on the network. We need to reduce them as much as we possibly can. We realize that they are required in certain instances, but we need to keep the number to a minimum. We need to valve control those bypasses with the right valve. And very often I see the wrong kind of valve used, or the right valve that's just not being commissioned properly. So that's absolutely key. We need to maximize the control range of the pump, so it speeds up to hit peak demand, but then backs down to its lowest position possible at times of low demand. Make sure that you've got that big delta, that you have accurate pump control so that it meets the demand, so that the system is reliable. And we absolutely need to not need to stop oversizing the plant rooms, which we do on a regular basis. We overestimate demand. We then oversize the energy sources as well. We use lower diversity than we should do in the calculations. Well, we don't add diversity into the cooling when we should. And all these issues compound each other, and you end up with systems that are literally, and I've seen this, 2 or 3 times the size they should be. And the moment you do that, those systems cannot back down because they're too large and back down to the lower demand periods in a day. Maximize the utilization of the thermal store, which I'll talk about on the next slide. Ensure thermal stratification in the thermal store. I'll cover that on the next slide. And the next bullet point. And we need to think, when we look at the plate heat exchangers, we need to look at the approach temperatures across those plates, because the approach temperature is simply the temperature difference between the flow in on the primary side and the flow out on the secondary side. That's the approach. The narrower that angle is, so the lower the degrees between the two, the higher flow rates we need, and generally the higher the return will be if it's heating, or the lower it will be if it's cooling. That obviously then decreases the delta T, which we've just understood is a bad way of doing things. Underfloor cooling gives you a much better performance, as does underfloor heating if it's a heating circuit. So look at underfloor wherever possible as the heat emitter, and then accurate pipework sizing, reducing the pressure drop per meter. It increases velocity, but it reduces the diameter of the pipes. And because these systems should be truly variable, we don't need to worry about erosion from high flow rates, because the high flow rate only occurs for a small period of time on that network. And then obviously, as you would expect, high levels of lagging, make sure we're not losing our cooling into the building where we don't want it, or into plant rooms, and so on and so forth. And then correct sizing of terminal units, and so on. And what a lot of people tend to do when I'm asked to look at problematic systems is they want to take me to the plant room. Come and have a look and we'll show you what's going on. And the correct way to work on these systems that maybe are underperforming is actually go to the opposite end of the system, to the very end, right to the heat emitters, and then start to optimize and work your way back to the plant room. And by the time you get to the plant room or the distribution area, that's when you've probably solved 90% of the issues that are creating your low delta T syndrome, and then you can just do the final corrections in the plant room. And then look at the temperatures that are actually needed in the building. It could be lower flow if it's heating, it could be higher flow temperatures if it's cooling, but look at what you actually need in the building. One of the issues, of course, with low delta T, it's bad on a heating circuit, but it's even worse on a cooling circuit, because you're already starting with a relatively low delta T that we need to maintain, that we need to not lose any of that if possible, because you have that lower delta T to play with. So when we look in the plant room area, I've given a generic plant room here where we're capturing cooling from different sources. So it could be maybe from free cooling somewhere, different applications. It could be absorption heat pumps that are capturing the waste heat and putting it into the system. And then you could have more traditional chillers and whatever cooling sources here. But the point of this graphic is, hopefully from the last slide, you got that we need to maximize that delta T on the network. So we've maximized this here. What we don't want to do at that point is then destroy that good work, that big delta T, by not controlling in the plant room correctly, or not hydraulically connecting things correctly, and we then destroy what we've struggled hard to achieve on the network. And one of the ways I like to do that is with bidirectional piping on the thermal store, so that the thermal store is connected with just 2 pipes and not 4, which is more traditionally. The problem with having 4-pipe connection, you get mixing in that thermal store and you lose your stratification, you lose your delta T. With a 2-pipe arrangement, we will have a delta on the store that is the same as on the network, and that will create a small stratification layer between the hot and the cool, or the warm and the cool, depending on the system. And you can monitor where that stratification layer is in that thermal store, and by using thermal probes in the size of inside of the store, so you know its location, but crucially, you also know its direction of travel. So why will it change? Well, think about it. If this stratification layer is moving up in the vessel, it means you're using your thermal store, your store of cool water onto the system. So that means that your demand here is greater than your output from all your cooling sources, because you're augmenting the cooling from the thermal store. So you may not do anything for a while, because you want to be using your thermal store. But when that stratification layer starts to get higher up in the vessel, you would then start another energy source to add additional cooling. And eventually, of course, you end up producing more cooling than you have as a demand. And what happens then is a reversal in the flow direction, and you start to fill that vessel ready for the next big peak. So the stratification layer starts to move down in the vessel. And again, you probably wouldn't do anything for a while and then start to switch off certainly the less efficient sources or the most carbon intense sources as that comes down. And obviously your waste heat or your free cooling, you leave that running as much as you possibly can. So that's how you would typically optimize the use of the energy sources based on their carbon implication and their cost as well, of course. So I'm just going to finish off with a few sort of projects that we've done. This one in Qatar. This is quite a traditional system, but I put it forward because it's so big. There's a huge amount of plate heat exchangers here, but there's a district cooling ring effectively around all those buildings. You can see we're providing the cooling, a lot of it coming from the surrounding sea. In Paris, the Louvre is part of the cooling network, and again, there's I think it's more than 52 kilometers now, the cooling network. There is a very large expansion program over the next 4 years as well to add more and more buildings. So the vast majority of the buildings in Paris will be on the cooling network. And one of the reasons, or one of the drivers for that, is really that graphic we saw earlier on with the heat island effect. And it's now it's been the city of Paris have determined it's mandatory if you are within I think it's a few hundred meters of the district cooling network. It's mandatory that you connect to that network rather than use an individual system, because they've recognized the problem of that heat island effect. This project I was at very recently, this is quite interesting. This is in Toronto. So basically it's called the Deep Lake Water Cooling System, and the majority of downtown Toronto is cooled via free cooling from Lake Ontario. And you find throughout the year the variation in the temperature of the lake water is hardly anything. It alters by 1 to 2 degrees between summer and winter, so it's always really cool. So it allows them to provide cooling through various different substations that we have in the plant rooms and then in the individual buildings, and it provides cooling to downtown Toronto, as I mentioned. M-Wave, who run that system, what they've now also done is integrated a number of data centers into that cooling network. So they provide cooling to the data centers, and crucially, they're taking the return temperature, their immersion cooling data centers, so they're getting return temperatures of 42 degrees coming back, and they're using that to partly generate hot water in the buildings during the cooling time, the summertime, and then in the winter time they're using that heat to provide some heating into those buildings as well, or at least at the start of that. So, and that is a very common application for us, the connection between a data center and a district cooling system. Just to show what that's like as a schematic, what we can see here is this data center sitting here. We've worked with a number of what's classed as eco data centers using renewable electricity to run the data center, and then we cool it via the district cooling loop that's sitting here between the district energy network, and then we're taking that return temperature, boosting it a little bit more to provide heating into the other houses. And as the predicted growth of data centers is showing, this will be a huge area of growth and we need to utilize that waste heat. And it comes back to my final statement is, again, what I said right at the beginning, really, that we need to stop thinking about cooling and heating and think about district energy. And we need to share energy across those different grids so that we're fully utilizing that district energy, that energy. And if we think of it in silos, we will always end up with waste energy. Whether that's waste heat going to atmosphere or waste cooling, it will make no difference. By connecting the two together, it then allows us to actually utilize all of that energy and waste the minimum amount possible. And my final comment would be, we're even seeing electricity coming more into that, not just by ORC as we saw earlier on, but as we introduce more and more renewable energy into the electrical supply, we find that the electrical price is fluctuating quite dramatically and very often goes negative. So what we can now do is utilize the energy that district energy companies have, be that in those pipes in the ground or with the sources that they're using to generate, like CHP, and they are starting to balance the electrical grid as it starts to fluctuate by turning on and off different energy sources, some of which may give to the grid or some may take from the grid. So we even now have some district energy companies who have one-to-one COP electrical boilers, and they switch them on when the electricity price goes negative because they get paid to use electricity, and then they will supply into the grid when the cost goes high because they get paid a lot of money to produce and give that electricity to the grid. So those district companies are now balancing the grid, the electrical grid, and reducing those fluctuations. So again, we have to remember energy is energy, and all those different forms need to be thought of as a whole, and how we can properly integrate those different forms into the sustainable city. So I'll finish my presentation right there, and I hope there's some questions to talk about at the end of the session. Thank you very much.
Yes, thank you. Thank you for the presentation. So we're at time, so I don't know how long, especially our speakers, how much time do you have? If any of you really need to jet off, let me know. I'll prioritize the questions for you. But okay, no running. So, okay. I guess we'll get to the questions for Patrick, since there's already some here. So I think, yeah, there are in the chat. I think maybe you've already read them, so I'll just hand it over to you.
Okay, thank you. I still have left 5 minutes, so if there are additional questions, please feel free to send them to me via email. And the questions from the chat are, what are the connection and disconnection fees for consumers? Do your customers have long-term contracts, and what are conditions for terminating the contract? The termination of the contract doesn't cost anything. The contract terms are around 15 years. We have prices for the construction cost subsidy around 465 euros a kilowatt at the beginning of the project. Then we have the basic price, that's around 160 euros for the kilowatt a year. And the, let's say the how is it called, contract price, that's around 60 euros a megawatt hour a year. We don't have any cost for the termination after these 15 years, but all the customers stay at the district cooling after that time. Okay, so the second question is, can you tell us a bit more about how you extract the cold heat from the ground source water around the tube tunnels? We extract it in a closed system. So I can show you clear the picture here. Okay. Hope you see it.
Yes, we do.
Okay. So first here on the right in the middle, there's a well. It's in public spaces, and we extract it close to the surface where the pipes are located, and we re-inject it the same way. And because you asked for horizontal, that's here. Yeah, middle on the in the middle picture, you see an horizontal drain well. It's a very big one. So we extract it via 3 drains and give it to a closed network and re-inject it the same way.
Okay, thanks. There was also another picture, I think, in between this one and the other slide you showed, the one with the section seen from above of exactly this one, where you have the horizontal drains. And I was wondering, because usually all the geothermal probes go vertically down and then turn, but in your case, you're going straight horizontally because you're at the exact level of the aquifer.
The horizontal drains are, can you see it's downstream, it says downstream, there are the drains, they collect the water.
Ah, okay.
Okay. And then it's here collected in this, in that big, let's say, pipe before it flows underneath the tunnel. And here's the re-injection with, again, 3 drains. And we place the pump here, as you can see the symbol.
Yep.
And then here's the pipe system in the streets.
Very cool. And the other question was about Dante's bath, because you mentioned that you can use that water during winter as a heat source. So it's an open air swimming pool that is also full in winter, which is not very common. But then you said also that you would heat up the swimming pool. So with which source? I missed that connection.
The pool, let's say the pool water has, I don't know the exact temperature, but it has above 23 degrees, 25, I think, and that's a preheating. So we take the water, heated groundwater that has around 18 to 20 degree. We preheat the pool water, and the rest is with district heating or heat pumps or so on. Something like that.
Okay, cool.
The data centers have around 2 megawatt of cooling demand, so we have enough heat for the, let's say, the floor heating for the bus depot and the heat pumps in the staff apartments and the Dante bath, the pools.
Thank you so much, Patrick.
There's a question in the chat from Evangelos as well, saying, can you please explain with an example, what exactly does it mean that the very nature of cooling gives us a lower delta T to work with? How would you compare that to heating? So typically, and I'm just talking generalities here, with heating systems, you're looking at maybe running at a 70 degree flow, 40 return. Sometimes it could be higher, but that gives you 70-40, gives you a 30 degree delta T. You can get higher delta Ts if you're running at higher temperatures, maybe as high as 40-45 degrees as a delta T. So that would be heating. But then when you look at cooling, you're much more likely to look at temperatures sort of at 12.6, 12.8, 14.8, that kind of thing. So giving you delta Ts of only 6 degrees. So you have to remember that's your starting point. So with heating, you may be starting with a 30 to 40 degree delta T. With cooling, you're starting at maybe 6 to a maximum of 8 delta T. So you've already, on cooling, got a much smaller delta T to deal with. So every bit of delta T that is effectively wasted through uncontrolled bypasses or whatever those different things I listed out, then you've only got 6 degrees left to play with, and you lose another couple of degrees, you've only got 4 degrees to play with. Whereas you can see on the heating side, because you've already by its nature got a much wider delta T, that's not to say it's not important. It absolutely is important, but there's more leeway. You've got more range that if you lose a few degrees here and there, then you've still got quite a lot of delta T left, basically.
Yeah, thanks very much. Yeah, that's I get it now. It's better with this example. Thanks very much.
No problem.
Yeah.
So are there any other questions? Otherwise, I guess I'll end it here. Thanks a lot, everyone, for the great presentations and for your attention. I appreciate it, and I think this gives us a lot of, interesting things to think about in the future, especially when building district cooling systems, and not to be forgotten in, as the mad dash to cool our homes come in the summer months. So thanks a lot. I appreciate it. And yeah, I'm sure see you guys somewhere else someday soon. So thanks a lot. And we'll send all the materials afterwards.
Thank you, everyone.
Thanks all. Thank you.
Bye-bye.
Bye. Bye.
Bye bye. Thank you.